Hi there, and welcome to this lecture on the scientific method. In this particular lecture, we're just going to be doing an overview of the major components of what the scientific method's about. All of you should have had some sort of background in the scientific method given to you when you were taking your science courses in the K through 12, and even science classes at the college level. If you've had any of those, you've obviously gone over the scientific method in those courses as well. So this particular segment is meant to be more as a reminder about what some of the ideas behind this are, and to get rid of any misconceptions you might have about the scientific method in action. So the big principal things we'll be going through in this lecture are what a hypothesis is, a theory is, and then what a law/principle is. So let's go ahead and get started. Let's go to the next slide. So the process of the scientific method, I like to say, always starts with curiosity. And to reach what's called a hypothesis, first of all, you need to be curious about whatever phenomenon you're interested in. Just garners interest, and I think you can think things through better when you're curious about it, and I think most scientists are. Whatever phenomenon they're researching, I think most scientists are starting off with curiosity. But you're going to need to start somewhere before you can ask questions about the phenomenon you are curious about. So you start to do observations and measurements, and that can differ entirely by discipline. Scientists in the earth sciences will be more outside garnering this data, mostly because that's the nature of the beast, so to speak. When you're dealing with the earth and researching its phenomenon, most of that requires you to be outside to do that. That's not true with everything in the earth sciences, but for a vast majority, you're definitely outside doing those things. That's probably true of some other sciences as well, like biology, especially if you're a field biologist. You'll be outside quite a bit gathering data about the life on the planet as well. And then there are a lot of sciences that really keep you in the lab. It kind of is funny how you see a lot of people depict scientists as wearing lab coats and holding test tubes to figure out phenomenon. And I don't think I've really seen very many scientists garnering that outfit. So, and it may just be because I'm in the earth sciences in particular, where mostly, if you've been to REI, you've probably seen basically what geologists wear out in the field. So it just depends on the science you're in as to how you will employ the scientific method. Now, once you have gathered your observations and measurements on the phenomenon you're interested in, you're going to start to ask questions about it. And most of the time, that's going to be more than one question. The questions need to be answerable. They can't just be the kind of questions that you throw out there that you know there's no way to get an answer for. And the reason they need to be answerable is because you need to employ the next part of the scientific method, which is being able to test your ideas. And you can't test them unless you can get an answer, or it's possible that you could get an answer from your data. So that's a very important thing to think about when employing the scientific method. Now, when a scientist is done observing and measuring, and they've gathered the questions they're curious about asking, and those questions are answerable, and once they've done their testing after that, based on the questions they are asking about their phenomenon, there's three things you can do after that. You can accept your answers that you've come up with. You can modify the answers you've come up with based on your prior experience. Now that you've done the testing, now you might feel like, oh, I think I might have asked that question a little bit differently than I should have. And you'll change your questions about and go again. Or you'll reject your ideas altogether, just say, oh, this is complete garbage. I don't know what I was thinking, after you do your experiments and testing and modeling and such, and just throw it out altogether. All of these things are good things to do in the scientific method, and you should be open to doing each and every one of them. Rejection just simply means you can just throw out thinking about that idea and focus in on what might be more correct as a result. So even rejection, even though at first might be disappointing to a research team or a single scientist doing the research, it ends up being a good thing because then it focuses their attention on the correct path. But once we get to that point of acceptance, and sometimes even with modification and rejection, there's going to be a point in time where the scientist is going to need to delve out and check with other scientists in their field of study whether their research is viable. They may accept their ideas, their questions, and they may have felt like they've proven their ideas. But really what counts in the scientific community is that the entire scientific community in that field of study accepts that research. So how do we do that? How do we end up getting that word out? Well, there's two major methods. One is publishing in a scientific journal. And every scientific discipline has them. In fact, usually several of them that you can publish to. Geology is no exception. You might be familiar with the Journal of Medicine that a lot of medical doctors publish to when they're doing research in the medical field. Well, all the scientific disciplines have something similar to publish to in regards to their research. And so that's one way in getting the word out. Sometimes, in fact, a lot of times the media outlets are also attached to these journals so that even though they're meant for the scientific community at large to read, the news media likes to know what the latest cutting edge research is in different topics, and so they'll read it and actually report these findings on the news. Unfortunately, when they do that, it seems like what they're saying is what science has revealed as truth, and not really considering the fact that perhaps that it's really just now being put under the scrutiny of the rest of the scientific community. For example, a new research discovery in diabetes. I'll do something that would be really familiar to a lot of you. There might be something discovered about diabetes that might help cure it, and so a research scientist in the medical field will publish in a journal, the Journal of Medicine usually, about their findings. And then the news media will grab it and then they'll say, oh, there's a new discovery on curing diabetes, and here is the findings. And they make it sound like it's gospel at that point. And it's not. It's just something that a research team has come up with in maybe the lab or wherever, and now they're just checking to see if the scientific community who does the same research that they do agrees with their findings. So you have to be really careful with how you listen to the media and how they report new findings in science, because sometimes they get proven false, and that's the whole point. That's why it's in the journal to begin with, to make sure it's viable before they move even further forward with it, with like human subjects and things of that nature. All right, so let's go ahead now and go to the next slide. And I want to talk about now what a scientific theory is. And that word theory is an unfortunate word, not really in the practice of it, but just that it matches the word theory in what the public is used to understanding what theory means. And let me explain what I mean by that. Let's say there has been a murder, and we don't understand how that murder occurred. So somebody's hired in to figure out how the murder took place. So they come in, they gather their clues, and they gather their evidence, and then you hear that they come up with a theory about what happened. That's what I mean. In the sciences, that wouldn't be a theory. That would be called a hypothesis. So what we just spent a whole lot of time talking about, that person trying to solve the murder mystery, that would be analogous to a hypothesis. But the general public tends to call it a theory. So you could see where the problem is. So when, let's say, someone in the general public hears that a new theory has been developed in the sciences for blah de blah, whatever it may be, it doesn't matter what, but they're going to hear it as, oh, it's not really foolproof. It's just their ideas about what's going on with that phenomenon, but it's just a theory, so it can't possibly have any merit. That's the unfortunate part, is theories in the sciences are solid. They're not anything like a hypothesis at all. They're not guesses. And that's, that's the unfortunate part about theory in the general English language versus the scientific language. And I think a lot of people, when they are trying to disprove science, I see this in social media all the time. I mention social media quite a bit because it makes me shake my head a lot. I'm sure it does you too sometimes. But you'll say, oh, but it's just a theory, so we don't really know. And a scientist reads that post and they just smack their forehead. Oh my God, they have no idea what's going on. And that's the problem with that. It's just a misconception. So you guys don't have that anymore because I've just taught you otherwise. And that's a good thing. And if you didn't already, if you already understood that, that's even better. But if you didn't, don't beat yourself up. You know now. And that's why you're in college, so that you can garner this kind of education and understand what's going on, and you don't have as many misconceptions that way going through life. So anyway, a theory in the geological sciences that we're going to spend a lot of time on is the theory of plate tectonics. A theory is well tested and widely accepted. So it's been tested in the lab. It's been tested by not only a scientific team who discovered it, by many other scientific teams afterwards as well. After they've published their data, a lot of other scientists get their hands in it and figure things out. And then over time after that, anything that comes up that's related to that theory constantly, continuously proves that theory correct over and over again. And theory of plate tectonics is a prime example in the earth sciences of just that. Every time we come up with a new idea about earthquakes, volcanism, plate motion, anything that's related to that theory, whenever we've understood it better, it always supports plate motion and the type of plate motion we see and the ideas we have behind it. So we're going to actually spend time learning about plate tectonics in a module coming up, and you'll see what I'm talking about with that there. All right, let's go ahead and go to the last slide now and talk about scientific laws / principles. Laws and principles are actually synonymous terms in the sciences. They mean exactly the same thing. Sometimes it's called the law of this, and sometimes it's called the principle of that. And so I wanted to make sure you knew, if you saw either of those terms, that there's really no difference in their meaning. They explain events in nature that occur with unvarying uniformity under ideal conditions. And the prime example that you would all probably know is the law of gravity. Now imagine yourself in a classroom. Obviously this course isn't set in the classroom, but you can imagine sitting in a room at SF State or wherever, and basically watching me at the front of the room. And what I always do when I teach this in person is I grab my keys and I lift it up with my hand, and then I just let go. And I say, with unvarying uniformity under ideal conditions of the law of gravity, these keys will fall to the ground every time. And that's how solid laws and principles are. Now, how does that differ from theory? A theory is supposed to be very solid, very well known, well understood, blah, 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 blah. The difference is in how specific laws are. Laws and principles are really single action type of ideas that you can write a equation to, a mathematical equation to, a very simple one like the law of gravity. Me dropping my keys from my hands to the floor, you can write one very simple mathematical equation to explain that motion. If you try to do that with a theory, it would be impossible. There's so many interweaving ideas and things that go on with it that it would just take a long time and probably be thousands and thousands of pages long if you even attempted it. So that's the difference. Laws and principles are basically tools to helping understand theories better. That's probably another really good way of saying it qualitatively. For example, we use the law of gravity to help explain a lot of different things that happen with the theory of plate tectonics that we discuss and describe. So it acts kind of like a tool to better understanding. It's things we can count on when we're doing research that we know does not vary. And we can use that to understand further processes of different things in the sciences. So I hope those explanations make sense. If you're still feeling a little foggy, just like with any lecture that we have, you have the invaluable tool in that you can rewind this and re-listen to me again. Whereas in a lecture course in the classroom, I don't rewind very easily. I guess I could repeat things and such, but basically you can re-listen to this, and a lot of times that will clear up any cloudiness you may have. Of course, the hard part about lectures like this is if you raise your hand right now, I have no idea on this side of the screen because I'm doing this well before you raise your hand and I'm not seeing you do it. So in that case, I always recommend you just write down your questions and email me right away after you listen to the lecture. So I say write down your questions because you may forget them as the lecture goes forward. With all the learning you may be doing during that time, your brain may get sidetracked otherwise. So and also a lot of times if you write down the question, I tend to answer it during the lectures because I've taught this so much in person. I can anticipate a lot of questions. Of course, you guys all have your own unique questions too. So, and I may forget to anticipate something that I've heard in the past as far as a question is concerned. So definitely feel free to email me. I'm very accessible via email. I check it pretty constantly. I may not answer you at 2 in the morning, but during the day, I'm pretty good at getting back to you quickly. So, all right, thank you very much, and I will see you in the next lecture.